Thank you. Thank you for the invitation. It's a pleasure to be here. So let me start by telling you a bit what we do in my group. What we do is we study biological systems across scales, in particular bacteria and sheep. That is what I'm going to talk today. And what we do is typically we start by proposing equation of motion for the individuals. So what equation of motion we should use to describe these individuals and the interaction. And then we try to see whether these equation of motions account for the macroscopic behavior that is observed. So basically, we start with a micro description, and we try to go to the macro description of the problem. So now the question is, what kind of mathematical models, or if you want, physical models, should we use to describe these biological systems? And I'm going to stress here that the main point is that the main point of the talk is to say that biological systems typically don't have one single equation of motion, but they are choosing to use, to behave differently, then they need to choose different equation of motion. So which kind of system? Well, for a few years we have been pushing this idea, trying to promote this theoretical framework. It's very simple, conceptually at least. The idea is that every particle or every agent has an internal control system that I'm going to think of that. Let's think of that internal control system as a mini brain. This mini brain is going to tell our agent which equation of motion has to be using. And we will use this framework to basically describe or understand bacteria, sheep, robots, whatever you give us, we will try to use this kind of framework. Okay, so let me explain you how it works. Let's suppose that we start by having some observations. So we have an experimental trajectory, very long. Here I make just with 3 motility patterns, but suppose that in this very long trajectory you have various motility patterns. Let's say you have 3. So the goal is to understand how you can build this mini brain. So the first thing is that this mini brain is going to be a Markov chain. That doesn't need to be a Markov chain, and we can have an evolving Markov chain and so on. But for the moment, I'm going to stay with just a Markov chain, a simple Markov chain. So now what you do is basically you try to compute for the distribution of time you see your pattern in this your particle in this motility pattern. Then you compute also the distribution of time you see in this pattern. So suppose this is, again, a very long trajectory. So from this distribution, then you will try to infer how many nodes you should put in this mini brain and how you should connect them. And say the idea at the end, once you have done this, is that when you are in one of the nodes that is black, you will use equation of motion 1 to describe the motion in space, in physical space of your particle. If you move to one of the right nodes, you use equation of motion 2, and so on. So then the idea, and something to keep to account, is that there are two spaces. There is physical space and there is an internal space. The internal space is whatever is happening inside this Markov chain in which node you are, let's say. But then that means also that you have interactions at the level of physical space, forces and torque, and there you can have also interactions at the level of the internal space, meaning that you can induce transitions from one internal state to another among neighbors. At least mathematically you can always do that. And we will also assume that there is a coupling between internal state and physical space. Okay, so this, of course, you can put in the computer and simulate. But for instance, if you have no interacting particles, this is easy to show that the problem is, the problems that you can formulate with this kind of framework are analytically tractable and exact solutions can be obtained. And when there is interactions, you can also do some analytics on this. Okay, but what I want to do is to tell you how you can apply this framework to real data. And I'm going to show you 2 examples. The first one is bacteria and the second is sheep. So let me start with bacteria. So I'm going to be talking how this pathogenic strain of Escherichia coli, the enteromorrhagic Escherichia coli, moves near a glass surface. So if it's not producing any stop on the surface due to hydrodynamic interaction, you are going to see that the bacterium performs circular trajectories, noisy circular trajectories. That means that it's revisiting the same area in space for a long time. So if something of interest is sitting on that surface, let's say a cell that this bacterium wants to infect, that is an inefficient way of exploring the space. But in general, what happens if you look at these guys, I mean these bacteria, is that they perform stop events on the surface, transient addition events, and then what you see is that they have this arc kind of shape. They may perform a stop, and by doing that stop, that allow them to break these circular trajectories and explore in more efficient way the surface. So let's see how we can understand and model this. So since the bacterium is performing these stop events, what you see if you look at the speed as function of time, you see that the speed is high, then low, high, low, and so on. If you look at a histogram of the speed, you are going to see that takes this form. It's a bimodal, and then you can use this local minimum to define a threshold and decide that define that when the speed is above this threshold, we are going to say that it's in a running mode or running phase, and is below that threshold that is in a stop mode or stop phase. Why we want to do that? Because we want to understand the statistics of the running times and the stop times. That is what you see here in the form of the survival curve in log ln. So here what you can see is that the distribution of runtime is straight line, meaning that it's an exponential, but the distribution of stop time is not an exponential. Now let's say that because you have defined two states, we want to describe it using a Markov chain, and we assume that we are going to use two states, one for the running mode and the other for the stop mode. If you do that, the problem is that basically you will get an exponential for the run times, that's fine, but also you will get an exponential for the stop times, which is not what we observed. So what can you do? You can enlarge your Markov chain. By having three states, you will be able to describe this kind of data. Now, you have to associate two of these states to the stop regime, and if you do that, then we are able to describe this. But now the question is, what are these two states that we are evoking and needing to use for the description? So if you go back to the data and you see what happens, often these bacteria were, when we were assuming that we were stopping, they were not genuinely stopping by doing this, and then detaching from the surface. So what we did is we defined two as the running mode. One is when they are in this state, I mean, basically not moving in the center of mass, but just rotating, and zero is absent of motion, meaning perform stop, and there is no translational or rotational motion. Okay, now, since we have a clear definition of these three states, what we can do is to measure for how long they are, I mean, this bacterium is in each of these states, and compute the probability going from state 0 to 1, 0 to 2, and so on. If you measure all this, you can get all the transition rate of the Markov chain, and you have a system that will describe the data I showed you before. So, but now the goal is not to describe only that, but describe how they move in space. So what we will do is to use this information that was coming from the Markov chain that was giving us the behavioral state of the bacterium to feed one equation of motion. I mean, this equation of motion, you have one equation for the center of mass, you have the other for the velocity direction, and what happens here is depending on what is your behavioral state, the speed, omega, and other variables or functions in this equation of motion is going to be changing. Okay, so of course you can perform simulations, but also you can understand what happens in this system in terms of probabilities. So you can try to describe what happens in this system by computing the probability of finding the bacterium in state I, position X, moving in direction theta at time t. So in order to do that, what you have to do is giving the Markov chain and this equation of motion, writing, I mean, a forward-Kolmogorov equation or Fokker-Planck, and that takes this form. This can be solved, and you can get, for example, without any problem, the diffusion coefficient. This diffusion coefficient is going to depend on how you wire the Markov chain and on the values of the transition rates. This is what I'm showing you here. This is the diffusion coefficient, a function of one of these rates. This is the rate K20, I mean from state 2 to state 0, which is the inverse of the running time. So as you can see here, there is it's not monotonic, and there are two limits that are easy to understand. One is when the is constantly running, so stops don't occur. Then you have these noisy circular trajectories, and that is relatively low diffusion coefficient. And the other extreme is when the bacterium is always stopped, and that gives you a 0 diffusion coefficient. And the good thing is that, as you see, there is a rate at which you get the diffusion coefficient maximized, and we found that these bacteria operate at the optimal frequency that maximizes the diffusion coefficient. And we check it in other bacteria, and that seems to work as well. So from this part, basically, what the message is bacteria, or this kind of bacteria, explore surfaces by performing transient addition event. And what I have shown you is that there exists an optimal stop frequency that maximizes the diffusion coefficient. Okay, now I move to sheep. So, and before going to sheep, I want to give you what, in my opinion, is the canonical view of collective motion. Many of you may disagree with me, but this is what I'm going to tell you. Suppose that you see particles, animals, or whatever, flocking, meaning everybody is moving in the same direction actively. So typically, what one assumes is that there is a velocity alignment mechanism, like, for instance, in the Big Shape model. What's the idea? Suppose that you are looking at this particle. This is our focal particle, the red one. What does this focal particle is going to compute the average velocity in this neighborhood and align its own velocity with the velocity of the neighbors. So it's going to do that. By doing that, everybody can move in the same direction. So there typically, I mean, most models and most studies, not all, but most, these assumptions. First assumption is that individuals are constantly moving and constantly negotiation on the direction of motion. Second, that there is no leader leading the collective motion. However, now what I'm going to show you here is an experiment with small group of sheep, 4, that you are going to see that these guys are here more or less static, not moving much, and then you are going to see that move in this direction in file formation. This is what you see. Then stop again. So again, they move more or less in file formation, and they stop there. And if we wait a bit, you will see them coming towards us. Yeah, I think this takes long, right? Okay, I think here they come. Okay, there they come. Okay, so now let me show you again. This is tracking data. This is from experiment. What I'm going to show you is basically the same. You will see the group static here, and you will see the collective motion phase with one individual. The individual that is going to lead the group now is the red individual. Then they are going to stop. They stay there for a while, and now you have another individual leading the group, is the purple individual. And then if you keep on observing that, you will see this repeats over and over. So these collective motion phases with different leaders at the front. Okay, so what are the features of the observed collective behavior? I think that there are two that are very obvious, is that these individuals go through two different phases. There are these stop phases, that we call it grazing phases, because they are mainly grazing while they stop, and collective motion phases, which are represented by this line in this plot. So basically what I'm telling you is that we are kind of changing our perspective of this collective motion by explicitly considering that the group stops and moves. Then we are also seeing, and I have shown you, that there are temporal leaders that are the ones that are leading the group during these collective motion phases. And because they are going from stop phases to moving phases, we can assume that the direction of travel is decided at the onset of the collective motion phases and is going to be given by the temporal leader of that collective motion phase. And finally, I'm going to show you that what they exchange is positional information. So very far away from what is typically a big shape model of velocity alignment models. Okay, so my first question, the first question I want to address is how individuals switch from static to moving phases and from moving to static. So we have a group, an individual, static, start moving, then it's going to stop, and then we want to understand how this happens. So in order to do that, we are going to do something similar to what we did with bacteria. So we are going to look at the speed as function of time. That is what you see here. And as with bacteria, you can see that the speed goes up, low, and then if you take the histogram, you can define a threshold and say that is above the threshold, the individual is going to be moving or running, and if below that threshold, the speed, we are going to say that it's not moving. Then we get this kind of signal, and we are interested in understanding the statistics of this time, the times the individual is moving and the times the individual is not moving. Okay, so this is what I'm showing you here. This is the distribution of run time, of moving times, and this is the distribution of stop times. This is in lin, and as you can see here, this is an exponential, but here the distribution of stop time, again, is not an exponential. So if, again, we go with this idea that because we are talking about moving and not moving, we may think of using two states, one for stop and that for moving, so a simple Markov chain with two states. We are going to fail because we are going to find the run times with an exponential, but we will also try to use an exponential to describe this kind of gamma shape that we observe for the distribution of stop times. What's the solution? As for bacteria, we can enlarge the Markov chain, and again, we need to associate two of these states with the stop phase or stop mode. Now, if you do that, I mean, you are able to describe the distributions I'm showing you here to the left, and now it's the same problem as before. You may ask yourself, what are these two states for the stop mode that we need to use for shift? So here we have defined the following. When these guys are stopped with the head down, we say that it's S1. When they are stopped with the head up, we say that it's S2. And when they are moving, we say that, they are moving. So that's that state. So having this definition, now you can go to the data, measure for how long they stayed in average in each of this state. You can measure the probability of going from one state to the other, and you can measure all the transition rates in the Markov chain. So that's fine, and that is going to give us, a model that will reproduce the individual statistics. That's fine, but the problem that we have for shift is that if you see, this is the behavioral experimental trajectory of chip 1, if you see what happens with chip 2, 3, and 4, this is what you get. So basically, they are all doing the same thing almost at the same time. So basically, they display a quite synchronized behavior. So how they do that, and how we can put in evidence that they imitate each other, and how we can quantify it. So in order to do that, we are going to use experiment with trained individuals. This is what you see here. So what you are going to have in the group is going to be one individual with a vibrating collar. So this vibrating collar, you can activate it from far away. When this collar starts to vibrate, this guy is going to look for a yellow panel, and it's going to move towards this yellow panel because it's going to receive a reward. So basically, the experiment is the following. You have a group of individuals. You have the trained individual is this one. You make the collar vibrate. These individuals start moving, induce the motion of some. And then what we ask is, what is the rate with which probability per time unit this individual is going to join the ones running, and with what probability is going basically to stay in the same state. We assume that this transition probability then depends on how many are running. That is, the running here is the final state, and how many are in the initial state, which is not moving in this example. So this is the experiment. Let me see. Yes, it's running. So here you see, so this is what we get. This is the trained individual. All the others are following. And with this experiment, you can measure when is at which moment each individual start moving, and then you can try to quantify these transition rates. So from these experiments, what we get is we get transition rates that you can model in this way. So the ones that were in the moving phase basically stimulate the others to perform a transition. The more are moving, the fastest the transition is going to take place for the ones that are, just not moving yet. And the more you have in your own state that inhibits you from performing that transition. Okay, this is what comes from this experiment. Then what happens if there is no leader? If there is no leader, as you can imagine, there needs to be some spontaneous transition rate, because if here I have nobody in the final state, this is 0, but however, as you can see in a group without leader, those transitions exist. This transition rate takes this form and is modulated by the number of individuals in your own state. This can be understood because otherwise the group will get accelerated. We can discuss that later. So now what we have understood how we can model the individual transition rate and how them coordinate this synchronized behavior, we can feed that to a simple model, will basically tell us when they are moving and not moving. And then what you can do is this. It's an experiment. This is a representation in 1D of this collective motion and this collective behavior, if you want. This is what you see from the experiments. Head up, head down, and then from time to time motion. And this is what you can get from the model. So I'm going to get water. Okay. So the statistics that you get is quite comparable between experiments and model. You can do some theory with that. I'm skipping that. But there are some things that you can learn from this kind of analysis, which is the following. Suppose one of the things that we can address with this, or we can ask, is what the purpose of moving or staying together. So here you may assume that being alone has some advantage. One of the advantages is that one avoids competition. You can go and pick up whatever you want that is on the field without competition with anybody. However, if you're alone, there is a drawback. There is another thing that you will need to do, which is you will need to be looking for predators, and you are alone on that. So you are the one that needs to be looking at predator all the time. Now, if you are in a group, what happens is that the time that you are in a non-moving state with a head up, which associated with the vigilant state, decreases with the group size. However, you can ensure that in the group there is always someone with a head up. So the time that there is at least someone in the vigilant state in the group doesn't decrease with group size. However, at the individual level, that is decreasing. So that gives at the individual level more time to do something else. Eating or doing whatever else. Okay, so now I want to show you what they do when they are in the collective motion phase. So I want to address two questions. How does information flow while the group is on the move? And what information is shared among the individuals when they are on the move? So I'm not going to enter into the detail how we got this. If you are interested, I have the slides and can explain a bit more about that. So I'm just going to give you the answers. So how information flow? We found that information flow through a hierarchical network where the individual at the front is basically passing information to the second follower or first follower, that depends how you want to count, and from the second follower to the third follower and so on. So you have that the interaction are highly non-reciprocal and the network is highly hierarchical. So what information they are exchanging? Okay, so what we found is that what they exchange is positional information and not velocity information. So there is one argument to convince oneself why is this. This is not how we got it, but let me illustrate why is that. If they will be using this network and exchanging velocity information, they cannot form a file. However, as you can see, if they here in this simulation, if they exchange positional information, they can do file formation. Okay, so now what we have is a model that reproduces what happens with sheep data. But why they do this? What can we do once we have basically understood or getting a model that more or less allow us to understand or to describe how they behave? Okay, what we found is that this type of behavior, sheep can take advantage of hierarchical and democratic strategies. And the reason is the following. By having a temporal leader, if that temporal leader knows how to solve a complex problem, for instance, know how to navigate this maze and coming from the entrance to the exit, by using the interaction network I show you, very hierarchical, and exchanging positional information, then is able to guide the entire group from the through the maze. If you exchange the information that you exchange is velocity, or you have an interaction network that is not strictly hierarchical, this does not happen. So this is the best way of guiding the group in an efficient way. And because you are changing continuously who is the leader, then what happens is that they can do what is called information pooling, and that allows them, for instance, to localize a given target in a more accurate way the bigger the group is. This is saturating, but it's growing with group size. Okay, so they can do both things. They can take advantage of democratic strategies and hierarchical strategies by using this kind of dynamics. With this, I hope I have still 5 minutes to, okay, good. So, okay, so something, if you go to large group and you put them in a very large surface and they are moving in from, some distance, you will see that they also form these files. So these files are not only observed for small groups. Okay, now I want to go to a question where we don't have still, and this is going to be difficult to get, very large experiment to measure how are what I'm going to call activation waves. So the idea is how does a large group of static individuals start moving? So I want to study what here I'm calling activation cascades. And basically the idea is that you have an individual that starts moving, and then we assume that this individual is particularly, may convince or induce a transition in this one and eventually in this one, but not, that interactions are not long range. So basically we want to understand how information is going to propagate from this individual to all the individuals that are in that file, assuming that they are moving. Okay, so the model is the following. So this is the speed, this is our individual, and the phenomenon that we are trying to understand is this one. Basically, how this red color is propagating towards the right. Okay, so this is very simple. So you have a kernel by which, one active individual may induce the the activation of an inactive individual, and the equation of motion is as simple as this one. If you are active, you move. If you are not active, you don't move. Okay, so there are two questions here I want to address. One is how can we understand the propagation of the front, and the second is which kind of, if there is a transition and what kind of transition is there. Okay, so for the propagation of the front, I want to go very quickly. You can do, what you may think that can be done in this particular case, that is constraining the problem and trying to describe it like in a PDE and using a kind of the standard formalism to understanding how a front propagates. And in this case, one finds that this propagation with this actual speed of the individuals, this is a propagation of the information of the green front, goes in this way. So goes not proportional just with B, but has a prefactor, and that prefactor is not 1. That is, you think about, not that obvious, at least not to me. And we see that we can, we get something that is in good agreement with the simulations. Also, there are two things probably to mention, that is when the individuals move at speed that is significantly lower than the speed at which information propagates, and the other situation is where they propagate at the speed that is comparable or larger than the speed information propagates. If they do it at small speed, what you are going to see is a kind of Fisher-like front that propagates. And basically, in that case, everybody is going to turn green, but you don't, you have an order. Let's say this is the first individual in the group, the second, the third, and so on. So they don't change in which order they are in that, in the group. But if you do it at this speed, which we call it the Selfridge regime, what happens is this. That means this individual can move ahead. This is the first individual, leaving others behind. So you can alter the order in that file, which allows you basically, if you are the one here, let others be closer to the predator. Okay, now I want to go with the part that I think is more interesting of this part, which is the following. So we have two states in this model. We have either the individual is active or is inactive. Now, imagine that what you have is we have this system, our speed when they move is they don't going to move. V is 0. That means that we have just two colors. We have this gray color and the green color. So independently of what is this distance, if this individual is active and you wait an infinite amount of time, you can ensure that this individual that is in state I will will turn into A. So basically the probability of finding this individual I at time to infinity in state I is 0. Now, if you allow this V to be different from 0, larger than 0, say, then what is going to happen is that you may start in this situation, and if you go to t to infinity, it's possible that you find this individual that is not, this pi is not strictly 0, but larger than 0. That means it can remain state I. In order to do that, you have to solve this equation. It's very, it's kind of straightforward thing to do, and get this expression, and here you can see, well, that if t goes to infinity, this goes to 0, and you get something that is different from 0. But here is what is interesting. Given this, now you can compare this probability and what is happening in this system with the system where particles don't move, but what happens is this one. This is this susceptible infective recovery model. So this is the infective individual, this is the susceptible individual, and this one can remain always susceptible if this one turns to R before, convincing this one of to infecting the susceptible individual. Knowing that, you can map one into the other, and now you can go into a 1D. In 1D, you have that this model should be equivalent to the SIR model. And in that case, in 1D, you are going to have that if the speed is negative, you get activation cascade that are always exponential. And if the speed is larger than 0, in this case, you have an infinite cascade. So in this case, nothing too interesting happened. But in 2D, you can expect that eventually in the SIR model in 2D has critical behavior. So this is what we explore. If here the mapping, however, in 2D is not exact, but you can hope that still give you what you expect in the SIR. So meaning critical behavioral is something that seems to be critical according to our numerics. So in here, what you have seen before is that you start the motion, and sometimes you get a very short cascade, and sometimes you get a very large cascade, as you can see here. So now, if what you do is you look at the distribution of cascade, you see something that in this case has an exponent of around -1 for this cascade. I'm not very confident about the exact slope, but this is significantly power lowish. In any case, it's not as exponential as in 1D, and according to the numerics and the analogy I have shown you, one may believe that the system exhibits critical behavior at the critical value of the velocity. Okay, so basically what I'm showing you with this part is a two-state active model can behave as three-state static model, and that the initiation to collective motion, understanding by what I show you here, from a static group to a group on the move, is a critical phenomenon. Okay, with that, I'm going to conclude. I hope that I convinced you that the framework can be used to understand, to model bacterial shift. What we have done is we converted a signal into a binary signal, and then what we have been doing is basically trying to get what was this mini brain. And for the two cases I show you, bacteria and shift, we saw that we needed to use 3 states, and the coupling with motion, gave us the behavior I show you. Okay, that's it, and this is, thank you for your attention.